All right, good morning, ladies and gentlemen. It is February 25th. It's Thursday, one more day this week. And today we are going to be taking a closer look at the structure of the atom. So we're going to be talking about Niels Bohr again. We're going to be taking a look at his model. And then we're going to look at some other ways to represent atoms and their atomic structures to look at how they're going to bond and whatnot. So let's go ahead and get into it. We are working today. Okay, let me go ahead and share my screen. Okay, we're going to be working today out of ICP, day 14, atomic structure. So here we have the Google PowerPoint, Google Slides, the fill in the blank notes, and then we have two little practices that we're going to be working on. I will tell you up front, especially for the Bohr model practice, you're going to need a piece of scrap paper to be able to do these on, or a separate sheet of paper, because there's not an easy way to do these on the computer. So a lot of what we're doing today when we're diagramming atoms, normally if we were in person, we'd be doing this on the board and on paper. But unfortunately for this, you're going to have to go ahead and get a piece of paper and complete this on a separate sheet, and then just message me that picture or email that to me, okay? So let's go ahead and take a look at the notes. So go ahead and open up atomic structures. And away we go. Now, normally we would review a little bit about the periodic table, and we would be taking a look at neon, okay? So neon, go ahead and pull up our version of the periodic table so we can all see. Resources, periodic table, okay? So if we open it up and we look here, we have neon right here. Neon is element number 10. Let's see, what do we have to answer? We needed to answer the following information about neon. Its atomic number. So its atomic number is number 10. The atomic mass. If you look there, it's a little hard to see now that there we go. It's a little bit easier. Neon's atomic mass is this number with a decimal, 20.1797. How many protons does neon have? So we would look at, to figure out the number of protons, we look at the atomic number again. So neon has 10 protons. To figure out how many neutrons, we have to take the atomic mass, which is 20.1 minus the atomic number. We're going to round this just down to 20. So 20 minus 10 gives us 10. So that means there's 10 neutrons. The total number of electrons, well, that again, atoms start off neutral. So if it has 10 protons, it starts off with 10 electrons. And then I need to know how many electron shells does it have, okay? In order to figure that, remember, we're going to look at what period it is in, what row. So neon is in period 2, which means it has 2 electron shells. And the last question is a little bit trickier, and that's how many valence electrons does it have? And we talked a little bit about this yesterday, but we're going to start focusing on this more and more, because this is really, again, going to determine how the atom is going to interact with other atoms. And we remember that neon is one of those noble gases. So it already has a full shell of 8 valence electrons. So everything in this row has 8. Normally I would give you this as paper, and we would be marking this up and putting some information on here. But a good way to know how many valence electrons, how many electrons are in the outer shell, is everything in group 1 has 1 valence electron. Everything in group 2 has 2 valence electrons. You have to skip the middle. These you have to look up. They don't follow a set pattern. But if we come over to group 13 has 3 valence electrons. Group 14 has 4, 15 has 5, 16 has 6, 17 has 7, and 18, with the exception of helium, 18 has 8. Excuse me. Now remember, helium is a noble gas because its outer shell is full, but it's so small that that shell only holds 2 electrons before it gets full. So, there's an argument to be made for helium really to be over here next to hydrogen, but because it acts like a noble gas, we group it over here with the rest of the noble gases. All right, let's continue with the notes. So again, today we're going to be talking about atomic structures. So we're going to look at the Bohr model. Should be a review. Remember, Niels Bohr was the one that said electrons travel in defined paths or orbits, kind of like you can see on this little animation. But remember, the key is that technically they don't follow a set path. Remember, Schrodinger came after and said, well, there's really just this electron cloud. That's the area that they're likely to be found. But the Bohr model is a good way to look at atoms, think about where the electrons are in terms of what energy level they're in, what shell. And it also allows us to have a really good way to compare different atoms. So even though Niels Bohr's model didn't end up being the final model or our final understanding of the atom, it still really helped us think about how to compare atoms and look at the similarities and differences between them. So why would I want to analyze an atom's atomic structure? Well, I would want to analyze an atom's atomic structure because that can help me understand its unique properties. How is it going to interact with other elements? Is it going to interact with other elements? What other elements is it most likely to react with? Okay, so we can make predictions about how things are going to combine and what might happen before someone actually goes out and does it, right? So it's an easy way, and again, it's an easy way to see similarities and differences between the different atoms. All atoms are made up of the same three parts: protons, neutrons, and electrons. Remember, the only difference, the only way that they differ is in the number of protons, neutrons, and electrons. So it'd be a good way to take a look at the atom structure. Just go to the next slide. There we go. All right, so we're going to take it all the way back to Niels Bohr. Okay, remember, Niels Bohr model is dated, but still a good tool to study atoms. He shows the protons and neutrons in the nucleus. So at this point, we did know about the nucleus. This is after Rutherford's experiment that found out the atom's mostly empty space. And he said that electrons orbit the nucleus in a fixed set path. Right? We know this is not quite true, but it's really good, again, a really good way to think and see about the model. So when we make our Niels Bohr models, they're going to look something like this. Now, especially for the bigger atoms, I don't mind, some people want to see all these little circles. You're going to put pluses in the ones that are protons and leave the other ones blank for neutrons. But the key here is if it's a really big atom, let's not draw the circles. Let's just put P equals and N equals for how many protons and how many neutrons, and then put a circle around that to represent the nucleus. Then we go ahead and we fill in the electron shells with how many electrons they can hold. Today we're going to talk about that number, each shell only has so much space, and therefore it can only hold so many electrons. But the electrons are around the outside in set orbits. So what information do you need to gather before you start building your Bohr model? Trust me, you're going to want to get all this information down first, and that way you don't have to flip back and forth between your periodic table and your Bohr model. So the first thing you want to figure out are the total number of protons, neutrons, and electrons for whatever atom you're going to diagram, because those are the components I'm going to be looking for when I grade these. So you draw a circle or circles, if you want, in the middle to represent protons and neutrons. So you can put a circle with a plus in it for a proton. If I see an empty circle, I will assume that's a neutron because neutrons have no charge. And remember, if it's a really big atom, don't bother drawing like 35 circles for protons and 35 circles for neutrons. I'm not going to count those. Just go ahead and put P equals and N equals in that circle, and I'll diagram that once we get to that point. Electrons go in the shells surrounding the nucleus, and like I said, each shell can only hold a specific number of electrons. So let's take a look at how many they can hold. And the reason for this is it gets crowded. Remember, electrons have negative charges, and if you have two negative charges close together, you're going to experience the repel force, right? Like trying to put the wrong side of magnets together. They're not going to like it. They need space. They need to spread out. So the shells on the out, like as you add more shells, they get bigger and bigger and bigger. The first shell is very small because it's close to that nucleus. There's not a lot of space. The next shell after that is much bigger, and then they get bigger and larger and larger and larger and larger. and therefore they can hold more and more and more electrons. So in this case, the first shell can only hold 2 electrons. It's the smallest shell. So that's why hydrogen and helium are really the only 2 atoms that can be satisfied to meet stability by having less than 8 electrons in its outer shell. The second shell does hold up to 8 electrons. The third shell is larger, can hold up to 18, the fourth shell 32, and the fifth shell 50. Sometimes they get pushed out once they get bigger, and so they can have a 6th or 7th shell. But the key here is that for general understanding, we're going to be focusing on atoms that have 3 or less shells, most likely. Maybe one that has 4 shells, but we'll see. So what we're going to do now is we are going to go back to our example of neon. And for this, I'm going to do my best to, let me actually pause this so I can hook up a mouse so I can do a little bit better about drawing this. Okay, so let me switch over to the pen tool. All right, so remember neon, when we looked at it, it had 10 protons. We subtracted 20 from 10 to get 10 neutrons. It has 10 total electrons. And we said that it had 2 electron shells. So what I'm going to do here is, again, I could draw the circles. It's going to take forever and it's going to be really hard. So I'm going to do the shorthand way. So I'm going to draw my nucleus in the middle. So just make a circle. And I put P, how many protons there are, and N for how many neutrons there are. So like I said, there are 10 protons and 10 neutrons in the middle. Oops. Oh, it's going to be bad. There we go. It's a little bit better. And then that completes the nucleus. Now I need to start putting electrons in the shells they belong in. So I'm going to draw my first shell. And that first shell is very small. Remember, it can only hold 2. So I'm going to put 1 dot here. There's 1 electron, 1 dot here. That's my second electron. Now it gets another shell. So draw that there. See, atoms are like onions. They have layers. Yeah, go ahead and sue me, Shrek. All right, so if I take 2 away, because I've already placed 2 of my electrons, that means I have 8 total electrons left to place, and I know that that second shell can hold up to 8. So go ahead and put those there. 1, 2, 3, 4, 5, 6, 7, and 8. And you want to draw these spread out as much as possible, because again, that's what the electrons will naturally do. Their negative charges repel, so they spread out as evenly as possible. And now we can see this is the correct drawing for the Bohr model of neon. All right, I can see again in my nucleus, I've got 10 protons and 10 neutrons. I could have drawn 20 little circles and put 10 pluses or pluses in 10 of them and left the other 10 blank, but I did the shorthand way. And then on the outside, I have my 10 electrons in their correct electron shells. So what's good about the Bohr model and what's a little bit, not so great about the Bohr model? Well, the pros are that it shows the whole structure of the atom. Not only can you see the nucleus, but you can see all the electron shells and all the electrons that they contain. It's a good, simple way to think about the atomic structure and visualize it. And it also makes it very easy to compare different atoms. What are some struggles, or what are some things that are not so great about the Bohr model? Well, it depends on what you need. If we're going to see, if you're looking at atoms and you're trying to figure out how they're going to bond together, remember that I said only the atoms in the outermost electron shell actually are involved with the bonding process. So all those electrons that are in fill shells on the inside, they're just basically there. They're not interactive at all. So you don't always need to know where all the electrons are on the inside, because they're not really involved in the reaction process. And then if it's a larger atom, these drawings can get huge. We can have some with like 100 protons and 100 some neutrons, and it just gets crazy. So again, that's why I usually do the shorthand once they get larger, but this is a good model to think about, you know, comparison and looking at the atom, but not necessarily necessary to use all the time. So like I said, we can use the knowledge of how these chemicals or how these elements are going to react based on their properties, based on their valence electrons, to determine how they're going to bond. Okay, so in order to do this, we need to take a look at the valence electrons each atom holds. So the number of valence electrons determines how reactive or not reactive it is. And remember, everyone wants to get to that magical 8 number, 8 valence electrons. That's super important. Everyone wants that magical 8 number. And only the noble gases get to start with 8. So noble gases are not going to be reactive because they have everything they need to be stable. Once these elements get to that or achieve that magical 8 number, or trick things into making it seem like they have that magical 8 number, we'll talk about that in a little bit, then they become stable. So atoms always want to move to it from less stable to more stable. So they're never going to lose or gain or trade electrons in order to make themselves less stable. It's always to go to a degree of more stability. So if you don't start with 8, like I said, you've got to figure out how to get it. So you're going to gain electrons. If you're close to 8, you're going to lose them if you're far from 8. Or if you're kind of stuck in the middle, you might end up sharing. We're going to see all 3 of those things take place. But everyone wants to get to 8. So if I wanted to take a look at how atoms bond, I may not want to do a Bohr model for all the atoms that I'm looking at. I may do or use what's called a Lewis dot structure. Lewis dot structure is just a very simplified way to see what element am I talking about and how many valence electrons it has. It doesn't tell you the mass, it doesn't tell you how many protons, it doesn't tell you how many neutrons, it has a whole lot less information. But it's a quick, easy way to say, hey, this is how these are going to bond, and this is how these are going to bond, based on how many valence electrons they have. So you write the chemical symbol in the middle, and you guys can see these examples down here at the bottom. And then the electrons are drawn as dots, and there's 4 sides to each element. So just think about the top, right, bottom, and left side as independent from one another. You place the electrons around until you run out of valence electrons to place. And here's the key. Each side has to get 1 valence electron before they double up. So if we were to look at nitrogen, nitrogen's in group 15. And I can, let me pull up this real quick just so we can see that again. Okay, we're talking about nitrogen right up here. Nitrogen is in group 15. So normally I would have you put a little 5 above this, but we can't really write on a digital document. So we'll just have to remember 15 has 5. So if we look at that, and how does that play out? Well, we drew 1 here first, then we went to the other side. We didn't draw the second one yet. So 1, 2, 3, 4, and then we start doubling up. Right? Think about it like rooms in the house. You got 5 kids and you've got 4 empty rooms. They're not going to want to share rooms and just leave rooms empty. Each kid's going to want their own room until they're forced to double up. Now there is a correct placement for these, but I'm not a stickler. As long as I see the correct number on the correct sides, that's what I'm really looking for. There's one of these spots is specifically a 1, one's specifically the 2nd and 3rd and 4th and so on. But I'm just looking for overall, do you have the right dots in the right spot? So let's go back to our example of neon, because like I said, this is one that we're just kind of using as a good example. And we're going to make a Lewis dot structure for this because we made a Bohr model, so we can see these 2 different models and how they look. But again, this one is so much simpler and it's so much faster because it's really just talking about the chemical symbol and how many valence electrons. So the chemical symbol for neon is Ne, so capital lowercase, right, neon. Oops, I'm not gonna write it over here. I'm just gonna do it on this little white spot. And then I'll put this here. It has 8. Oh, wow, that's not an 8 at all. Good job. There we go. That's even worse. All right, it has 8 valence electrons. So I'm gonna start here at the top and I'm gonna draw 1 dot. There's my 1 valence electron. Then I'm gonna come to another side. Here's number 2. Go to the bottom. Here's number 3. Go over to the left. There's number 4. Now each side has one, so I can start doubling up. Put another one on top, there's 5. Another one on the right for 6. Another one on the bottom for 7. And another one on the left for 8. And now I can see all 8 electrons. This has a full valence electron shell. So again, neon is not going to need to react with everything because it already has that magical 8 number. So what's good about a Lewis dot structure is it just shows you what you need to know sometimes. The valence electrons, that's going to be used to help you understand how they're going to bond. It's a very simple, easy way to kind of get a good amount of information very quickly. What are some drawbacks to the Lewis dot structures? Well, they don't show the full atomic structure. So if you were to, what do I mean by that? If we go back to our periodic table, if you were to look at, let's say, neon, like we just looked at, and xenon, they're going to look identical in terms of their Lewis dot structure, but they are nowhere near identical in terms of atoms. Okay, neon only had 2 electron shells with a total of 10 electrons, whereas xenon would have 1, 2, 3, 4, 5 electron shells and 54 electrons in them. So again, if you were looking at the Lewis dot structure for those would look nearly identical. But if you were looking at the Bohr models, then you get to see how big of a difference there are between neon and xenon. So again, you got to be careful. There are good reasons to use each set, but if you want to know how they bond, Lewis dot structures are the way to go. All right, and that's really it for atomic structures, okay? What we're going to do now is we're going to move over to the practice so that we can work on how to practice and make more Bohr and Lewis dot structure models, okay? So let's go ahead. Now I'm going to switch over to the practice. So I'm going to open back up my classroom. Okay. I'm going to go back to here, and we're going to start off with the Bohr model practice right here on the right. Now, like I said, you're not going to be able to draw on this, so this is one you're going to have to do on a separate sheet of paper. But what you're going to do is you're just going to simply make the Bohr diagrams for each of these, okay? There are only 8 of them, so it won't take you very long. And this will really help ground the idea of how to make these, because you're going to need to know these for the quizzes and whatnot. So I'm going to try and pull up a little whiteboard, if I can. Let's see. Share screen, whiteboard. Let's see what this looks like. Okay. I've not used this before, so we'll see how it works. The first one we're going to do is beryllium. Okay, so again, take a look at that periodic table. It's good to have up at all times. Beryllium is element number 4, Be. Okay, so again, we need for Bohr models, rather, excuse me, we need to know the number of protons, number of electrons, number of neutrons, and how many shells it has. Okay, so if I'm looking, and actually let me share this. So if I'm looking here at my periodic table, I can see beryllium, how many protons does it have? It has 4, because that's the atomic number. That means it also has 4 electrons. If I do a little bit of math, let me zoom in here. Beryllium has a mass of 9.01218. So we're just going to round that down to 9. So I take 9 minus 4. So beryllium actually has 5 neutrons. 5 neutrons. And how many shells does it have? Well, it's in period 2, so that means it has 2 shells. So now let's go back to that little whiteboard thing. Okay. And let's go ahead and I'm going to draw a circle. Maybe. There we go, draw. Oh, can I just make a circle? That would be really nice. Hey, look at that. I bet I can even, yeah, there we go. I'm going to have nice, neat circles. Look at that. All right, so we got a circle. That's the nucleus. All right, and inside the nucleus, we have 2 numbers. We've got, oh, I can even write with text. Look at us go. Look at this technology do its thing. Okay, so we have the number of protons, and for beryllium, we said it was 4. Then we have the number of neutrons, and we said for this, it actually had 5. So there's our numbers. So that's our nucleus. Now I'm going to go ahead and draw the first shell. See if I can kind of make that nice and neat. And now I can just use this to draw my electrons. The first shell can only hold 2. We know that beryllium has a total of 4. So 1, 2. I'm not going to be the same size, but that's okay. Need that one a little bit bigger. There we go. Okay, so that first shell is now full. So now I need to draw a second shell. Okay, more or less good. Go with that. Just squeeze it down just a little bit. Okay, there we go. All right, and how many electrons does it have left? Well, it had a total of 4 electrons. So that means that it only has 2 electrons to go in that last outer shell. That's terrible. There we go. 1, 2. Okay, and we can see here we have the atomic model, Bohr model for beryllium. Got the nucleus, the number of protons, the number of neutrons, and then we filled the electron shells with the correct number of electrons. That first shell only holds 2. The second shell can hold up to 8, but we only had 2 left to put in it, so therefore it only has 2. And what does that mean? Well, that means that this one and this one are both valence electrons. And does that make sense? Well, if we look at beryllium, beryllium is in group 2, which means all of these in group 2 have 2 valence electrons. So that is correct. That's another way to check your work. Did I get the correct number of electrons in the outer shell? So that's how you do that one. That leaves you with 7 left to do, or excuse me, 9 left to do. I guess there's 10 down here. And go ahead and skip number 7 because that's a double. Don't do 2 berylliums. Let's just make this one boron. Okay, make number 7 boron. Sorry, I always forget that edit, but go ahead and I'll see if I can re-upload this maybe with the corrected one. All right, so that's it for Bohr models. Like I said, I'm going to let you finish that one up. Let's go ahead and head back to the classroom. And I just want to peek at the other practice as well for the Lewis dot structure. So go ahead and open up your Lewis dot structure one. Let me share the screen. Okay, here we go. So I'm just in the Lewis dot structure one. So at the top we have elements. You just got to type in their chemical symbol. Tell me the total number of electrons, how many valence electrons it has, and then again, this is going to be something we're going to really have to figure out how to do on the computer. As of right now, there's not a good way. So just you're going to have to write these on a separate sheet of paper and turn that in. Don't worry about number 2. You can attempt this if you want. This is what we're getting into next week. We're going to talk about how atoms bond together. So a lot of this is dictated, all of this actually is dictated by how many valence electrons it has. So you might be able to kind of piece this together, draw the Lewis dot structures for each, and then kind of think about how they might form or how they might bond together. But like I said, we'll get to that later. So potassium chemical symbol is K, capital K rather. There we go. How many electrons does potassium have? Well, if we look at, I should just keep this up. If we look at our periodic table, here's potassium, it's K. Oops, too zoomed in. Right here, and it has element number 19, so that means it has 19 total electrons. So that's the total. Of those 19 electrons, how many are valence electrons? Well, we have to go back, take a look. Right here, it is in group 1, right? The first family, and they all have 1. So that means it has 1 valence electron. And so then I would draw my K, and I would just put 1 dot, and I'll just put a period by it, just as a way to put a dot. You can't move the periods anywhere else, but because I only had 1, that's a good way to do the example for the video. Okay. So you guys have the rest of this chart to fill out. Like I said, you can attempt the bottom if you like, but that's just kind of extra and thinking ahead. This is what I'm looking for. All right, symbols, total number of electrons, how many are valence, and Lewis dot. And again, just to go over the valence, everything group 1 has 1, group 2 has 2, skip the middle, 13, 3, 14, 4, 15, 5, 16, 6, 17, 7, and 18, 8, with the only exception being helium. So at this point, I'm going to set you guys loose to finish that stuff up on your own. Okay. Nothing else from me for today. If you haven't got done any of your quizzes and you're starting to fall behind, make sure you get in to the building and start working on those. And if you have any questions, as always, reach out, nick.welsh@excelcenter.org or technicwelsh on Facebook. All right, guys, thanks for zooming in, and I will see you next week when we start talking about bonding.